So welcome you all to this course. So the main objective of this course is to provide knowledge of partial differential equations. So which is related to the mathematical modeling of some physical phenomena. So why to learn mathematical methods? Because it is useful for solving some partial differential equations. So let's start with the definition of partial differential equation. So definition of partial differential equation, which is also known as PDE. So a PDE is an equation. So it is an equation where the unknown is a function of is a function u of several real variables through its partial derivative. So it can be written as in this form. This is the function of the derivative of du k dk minus 1 u dot d square u of x equal to 0. So here x is a vector. This x is a vector here, and u is a unknown function. Is an unknown function, or the function which we want to determine, or it is the function which we want to determine. And this whole term with we can represent it in the form of as ux ux2 dot uxn. So this is the basically we can call it as a gradient of u. We can write this format like this one, ux as dou u by dou x1, ux2 as dou u by dou x2, and uxn as dou u by dou xn. And for higher derivatives, we can write dou ju. This is the higher order derivatives. Higher order derivatives. Example, for example, u x1 x1, u x1 x2, u x2 x1, or u x1 x1 x2. So these are the form of the higher derivatives. So the main question is like why we need to study partial differential equation. Partial differential equations. So these are the main question. The answer is because they are all everywhere around us, because they are finding applications in real life. And and second opinion is because they are interesting from mathematical point of view. First is application in real life, because they find application in real life, and second option is that it's interesting from mathematical point of view. Now let's see some examples of partial differential equations. Examples of partial differential equations. So we will write partial differential equations for the function of two variables which depend on two variables such as which are x1 and x2. So we can write x is equal to x1 and x1 comma x2, which is the element of real space. This is the vector x here, which you saw earlier in the equation, and so we can write it also as a function of x and t. So this also belongs to the domain. Now let's see the example. So let's see the example of these equations. So first equation is this format: ut plus ux equal to 0. So this is this is the transport equation. Now other equation is ut equal to uxx. This is the heat equation. Other example is utt equal to uxs. This is the wave equation. The last example is utt plus uxx equal to 0. So this is the Laplace equation. So in order to solve this type of problems, we need method of separation for solving the heat, wave, and Laplace equation. We have various methods for solving this type of equations. Now let's see one by one. In the upcoming lectures also we can see how to solve this type of equations. So let's start with some few techniques for solving these type of equations. So what are the methods for solving these equations? So first method is, let's discuss about method of characteristics line. So this is the first method we are going to discuss. So let's start. So we will start with the method which is applied to transport equation. So because it is the simplest one, because the transport equation is the simplest one, let's apply this method, that is the method of characteristics lines, to this equation. So in the simplest form, we have a transport equation written as ut plus ux equal to 0. So for u is the function of x and t, x is the element of real number here, and t is the element of real numbers. So in more general form, if you write this equation in more general form, it can be written as ut plus b dot dx u equal to f. So this is the representation of more general form of the transport equation. This equation is for u equal to u of x dot 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 of x and t, and x bar is equal to x1 dot 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 xn, which is element of this, which have n components, and which is the element of n-dimensional equilibrium space, and this is the also element of the equilibrium space. And this dot here is the scalar product. This is the scalar product in this expression. So here here b is the given vector here, which can be b1, which ranges from bn and is the element of the equilibrium space, n-dimensional equilibrium space. And this term, that is dx u, is the gradient of u with respect partial variable of x. So we can write dxu as ux1 ux2 dot 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 uxn, and we can write simply in this format, that is b dot dx u is equal to b1 ux1 plus b2 ux2 plus dot dot bn uxn. So that is, and here f is the f of x1 dot 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 till xn, which is a given function. This is a given function. We will see its importance in the coming minutes. And this is the function of the Euclidean space, that is this one. Now let's talk about the physical model, that is where this equation comes from. Now let's discuss about the physical model of this equation. So the function in the equation u represents the function u represents in this equation the mass density of a substance, contained into a fluid, and transported by fluid itself. So we can write u as the function of the that is the mass density, which is the function of x and t. And in the expression, so this is the for u. Now let's talk for b vector. So here b is a fixed vector. So b is a fixed vector. It can be thought of as a velocity of a fluid, which can be maybe it can be thought of as a velocity of a fluid. Which is constant in time, in time. So we can write b as this one also, b1 dot till bn, and the last f function. So this was for b. Now let's talk for f in the expression. So here f represents f of function of x1 dot dot till xn, and it represents the source or sources which supply the substance into the region occupied by the fluid. So these sources are constant in time. So the equation can be derived by imposing that mass is preserved, that is due to the conservation of mass, for every subdomain contained into the region occupied by that fluid. So let me represent in a graphical or diagrammatic way. So this is your suppose region of interest, that is this is our subdomain, and here this is our source supplying the particles, and substance can also flow from this boundary of this subdomain. Substance can flow from this boundary of this subdomain as indicated here, and we can write the equation first with this, that is the variation in time of substance contained into this subdomain. So that is, this equation can be written as d by dt integral over subdomain rho dot dx. So basically this indicates variation in time of the substance contained into subdomain, and this is equal to integral over subdomain f dot dx. This is from the source of mass. This equation, this expression comes from the source of mass minus integral mode over the boundary. This is the integral mode over the boundary, rho dot v dot gamma. This expression comes from the flow through the boundary, from flow through the boundary. Here let's simplify here. Here v dot is the velocity of fluid, and here gamma is the unit normal to the boundary, like this one, unit normal to the boundary. I hope you're understanding. And we have to do some manipulation here in order to solve this equation. Let's do the manipulation thing. So first thing is that in the equation of this one, like in the above expression, this equation, this thing, rho of xt dot dx, we have to bring this expression inside, like we have to bring this derivative inside this integral, and we are going to get the expression as this thing, rho t of xt dot dx. And the second manipulation we have to do is we have to consider the vector field, like in this expression we have to take this as a vector field, this thing as x, which is the vector field, and it can be written as in this form, which is the divergence theorem, or we can call this is the divergence theorem, or we can call it as a Gauss-Green theorem. Now we can solve the vector field or represent the vector field like something like in this format, that is x equal to x1, x2 dot dot till xn, which is the divergence of x, and it can be represented as dou of x1 by dou x1 plus dot dot till dou of x or n till dou xn. And here in the expression v and b are constant, the main expression which we have written earlier. So we can write divergence of the vector field, that is x, as divergence of rho v equal to divergence of rho b. Here b and v are constants, and in order to more simplifying, we can write this above expression in this format: rho b1 plus dot 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 till dou xn of rho bn. Or after further simplifying, we can write it as dou rho dou xn b1 plus, because b1 is constant and density is varying here, plus dot dot till dou rho dou xn bn, which is equal to d of x rho dot b. Now we will rewrite this manipulation in the conservation of mass equation. Now after rewriting, we are going to get this expression as, subdomain rho of t equal to f minus dou x rho dot b, which can be written as rho of t plus integral over subdomain dou x rho dot b equal to f. And after further simplifying, we are going to write it as in this format: rho t plus dou x rho b equal to, this is source, that is f. Now replacing rho with the u, we are going to get in this equation, we are going to get the equation, this thing, ut plus dx u dot p integral over subdomain, that is f. So this equation must be hold for region where the fluid lives. That is, we can overall write this expression as mu t plus dx u dot p equal to f. So this is the general form of our transport equation. Now we have to decide the method to attack this equation. First, we can see in the form of Cauchy problem method, that is Cauchy problem. So this is the initial value problem for ordinary differential equations. So how the density of mass, which modeled by function u, evolves with starting datum. So our main is to determine that how the density of mass which is modeled by function u evolving from starting datum. So we have to solve this boundary condition, that is ut plus b dot dxu equal to f, and the second boundary condition is c of x 0 equal to g of x. So basically, you have to solve this initial boundary conditions, and here x is the element of the Euclidean space, and t is greater than 0, and here x is the element of the n-dimensional Euclidean space. So we are going to see that this problem is well posed. That is, it means that we are in a very lucky situation in which the existing solution is unique, continuous dependence on data. That is, there is a small perturbation produces a small perturbation in data, and this solution is explicit in nature. And when this f is equal to 0, then we call that equation as a homogeneous equation. That is when f equal to 0. So we are going to treat separately the following cases in the upcoming lectures. That is, in exercise part, we are going to solve the solution of this equation. That is for the following cases, and the cases which we are going to discuss is for one-dimensional homogeneous case for this transport equation, one-dimensional homogeneous case. Second case we are going to see is n-dimensional homogeneous case, and third case we are going to see is n-dimensional non-homogeneous case. So in the one-dimensional homogeneous case, x is element of the Euclidean space, and here f is equal to 0. In n-dimensional homogeneous case, x is the element of n-dimensional Euclidean space, and here f equal to 0. And in this case, that is in non-homogeneous case, x is the element of n-dimensional Euclidean space, and here f is not equal to 0, but it is arbitrary. This is arbitrary. So this marks the end of our the first lecture, and in the second lecture we are going to solve some exercise problem which will further highlights the application or the concept of this lecture. So for now, thank you.